Welcome to Learning with Philemon. In this video, we will be looking at the assumptions made in the ideal gas law and the difference between ideal and real gases. In the video Molar Gas Volume, we saw that at room temperature 25 degrees Celsius and pressure 1 atmosphere, 1 mole of a gas has a volume of 24.0 decimeters cubed. This is the constant used at GCSE level chemistry. However, at IB and A-level chemistry, we use the constant at standard temperature and pressure, or STP. This will be discussed in the subsequent video. But how can you determine the volume of a gas at different temperature and pressures? The equation you can use is the following. Pressure P multiplied by volume V is equal to moles N multiplied by the gas constant R multiplied by the temperature T. Watch the subsequent video to see how this equation can be applied. This equation can only be applied if some assumptions are made. The first assumption is that the particles are assumed to be in constant random motion, as represented by the black arrow. They obey Newton's laws of motion, moving in straight lines and changing direction only when they collide with other particles or the walls of the containers. The second assumption is that these collisions are elastic. This means that there is no loss of kinetic energy upon collision. The third assumption is that the volume of the particles is considered to be negligible compared to the volume of the gas. In other words, the volume of the atoms or molecules is considered to be zero. As a result, the identity of the gas particle is irrelevant. The volume of a hydrogen molecule is considered to be the same as the volume of an oxygen molecule. In this diagram, we see a container consisting of gas particles. The volume of the gas is equal to the volume of the container. As the volume of the gas is much greater than the volume of the particles, most of the gas consists of empty space, as can be seen in the diagram. The average intermolecular distance, depicted by the green arrow, is much greater than the size of the gas particles. The final assumption is that the particles experience no intermolecular forces. This means we are not considering London forces, dipole-dipole forces, or hydrogen bonding between the atoms or molecules. We will discuss this more in detail later. Although this equation is used at IB and A level, in reality most gases do not behave ideally. Only some gases behave ideally, and only at certain temperatures and pressures. We need to be aware of these limitations. Let's start by discussing the effect of pressure on the behavior of gases. As the pressure increases, the volume of the container decreases at constant temperature. See more details in the gas laws video. At very high pressures, the intermolecular distances are comparable to the size of the particles or molecules. The assumption discussed in the previous slide, that the volume of the gas is negligible, is no longer valid. We can no longer assume that the volume of the particles is zero. In fact, the volume of a real gas is higher than the value predicted using the ideal gas law at high pressures, as the volume of the particles is significant. The small separation between the particles also makes the intermolecular forces significant. The attraction between the gas particles actually reduces the frequency of the collisions with a container's walls. This reduces the pressure. Note that pressure is the force exerted over an area. The fewer collisions against the container's walls, the less force is exerted and the less pressure there is. Now let's see what effect temperature has on the behavior of gases. Temperature is a measure of the average kinetic energy of the particles. The higher the temperature, the faster the particles will be moving on average. In the diagram, the size of the arrows represents the magnitude of the velocity of the particles. When particles have enough kinetic energy, they can overcome intermolecular forces even if they are close to each other. However, at low temperatures, the kinetic energy of the particles is low and the intermolecular forces are significant. If the intermolecular forces are strong enough, condensation occurs. The gas turns into a liquid and thus will not behave like a gas. Having a high pressure and a low temperature means that particles are close to each other and do not have enough energy to overcome the intermolecular forces. Now let's see what other factors other than pressure and temperature may cause a deviation from ideal gas behavior. The identity of the gas is important. Polar molecules deviate substantially from ideal gas behavior because they contain a permanent dipole. For more on permanent dipoles, please check out the intermolecular forces video. Because of this permanent dipole, there will be a strong intermolecular force between the molecules. The assumption that the intermolecular forces are not significant cannot apply. Ammonia, NH3, is an example of a polar molecule that would deviate from ideal gas behavior even at high temperature and low pressure. Larger molecules also deviate from ideal gas behavior as the volume cannot be ignored. There are a few atoms and molecules that follow ideal gas behavior at high temperatures and low pressures. These are hydrogen, H2, oxygen, O2, nitrogen, N2, helium, He, and neon, Ne. Note that these molecules or atoms are small and nonpolar. In summary, ideal gases follow the equation PV equals nRT. The gases H2, O2, N2, He, and Ne follow ideal gas behavior at high temperature and low pressure. These gases deviate from ideal gas behavior at low temperature and high pressure. Polar and large molecules deviate from ideal gas behavior at most temperatures and pressures. Thank you for listening. If you are interested in reading a more in-depth analysis, please check the link in the description. Stay curious.